here's a little bit about exponential functions. It very much mirrors what's in the text, but I wanted to just give you a video about it in my own perspective. So we started out thinking about compound interest, and we're still going to think a lot about compound interest for quite a while. But the thing we were led to was the idea of taking some number. In this case, I'm going to think about 2 first, and raising it to different powers. We had things like 1.05 to the time or something like that. But let's strip it down to the sort of the most mathematically basic example, which is let's take the number 2 and let's repeatedly raise it to a bunch of different powers. Well, probably the first thing to do is not so much analyze the whole function all at once or graph it, but to do a tabular form, and I think I'm going to use a different program to talk about that. So let's say x, let's just take the numbers from 1 to 10, and let's say y is going to be 2 raised to all those numbers. Don't worry about the syntax of this. I'm not trying to teach you MATLAB. It's just a very convenient way to get the table. And those are pretty familiar, at least the first few are the powers of 2. If we put them together in a table, there's the data, there's our x's and there's our y's. And the first thing that most people notice about this is how quickly these numbers grow. They start out in single digits, but by the end, after only 10 tries, we're up to the thousands. And that's a very important thing about how these functions work. And let's look at what happens when we plot this thing. We get a graph that starts out quite small. Look at the scale here. To accommodate this point up here, the scale has to be up to 1,000 and more. And it starts off quite small. You can barely even see the first values because it grows so strongly over here at the end. And that's just going up to x equals 10. So exponential growth is, even in popular culture, people say, oh, something was growing exponentially. They very rarely mean that in an accurate mathematical sense. They usually just mean it was growing quickly. But there's some truth to that exponential functions do grow quite quickly. Well, what about if we had different x's? What if we had, let's say, minus 10 to 10? And let's make this a little bigger. Okay, and then let's say y is 2 to those guys. Well, now we're starting with very small numbers, because 2 to a negative power is a fraction. So 2 to the minus 1, for example, is right here. That's 1/2. 2 to the minus 2 is not really 0.000. Oh, sorry, 2, what am I saying? Oh yeah, this is confusing. Aha. It's like, what's going on here? The reason, so this is another thing about exponential functions. It's doing this in exponential notation. It's saying this is 1,000, so 1E003 is 1,000 times all these numbers. So it ends up with 1.024 times 1,000. And right here is 1/2. That doesn't look like 1/2, but 0.0005 times 1,000 is going to be 1/2. This is a rounding of 1/4. It's really 0.00025 times 1,000. And so even using exponential notation, it's having a hard time even displaying in a table what these values are. Let's get it to do a little better job. Now it can actually show you 1,024 in exponential notation, 512, 256, down to 1, 1/2, 1/4, an 1/8, a 16th. And you can see how tiny those are. If we do the plot command again, then for most of the time it's just absolutely hard. It's impossible for this thing to plot accurately to give a good sense of what's going on. One of the things we're going to discover eventually is a better way to plot these expressions so that you don't just have a few meaningful data points and then the rest of them that just look identical because they're so small and compared to these big values at the end. So let's look at one more x values. Let's say start from 0 again. And maybe let's not go so far. Let's step up by, let's say, quarters, and just go up to like 3. And we don't need that many decimal places anymore. So there's x, a quarter, 1 to 2 to 3. And let's say y is these numbers. Now I'm taking things like 2 to the 1/2. That's a familiar number. That's root 2, and that turns out to be the 1.4142. That's fairly familiar. 2 to the 1/4, less familiar, but we have an idea. That's the 4th root of 2, and it's in between 1 and 2 to the 1/2. And so now we're getting some more manageable numbers, but at the expense of not getting integers anymore. If we plot again, now it's actually a pretty manageable graph. You can still see that it's bending upward. It grows faster as you go, but it's not this extreme kind of thing where it was really flat and then really steep at the end. So the great thing is it makes sense to put in any number whatsoever for x. It's going to be a little hard to think of it as a sort of a nice simple root, but it makes sense even if I have like x is 0.01 to 3. Let's not print that. And let's not print that. That's going to be a lot of values. Now we get is plotting an incredible number of values in here. It's 300 different values of 2 to the 1.01, 1.02, 1.03, 1.04. All those values are in here, and it makes for a smooth curve called the exponential function. So let's graph it on this one. The graphs tend to look prettier here. Oh, I think I just need 2 to the x. So there's a graph. Okay, so the default goes from -5 to 5. That's pretty reasonable. And what I want to do is I want to compare that to some other graphs. That's 2 to the x, and I've been focusing on using 2 as the base for this exponential expression. But let's go a little in a different direction. We'll keep the x's from -5 to 5, but I'm going to add in 3 to the x as another graph. Now, notice what happened. The scale, if you look carefully, the scale has actually changed. This is the 2 to the x. 2 to the 5 is about 32. 3 to the x grows significantly faster, and it's way up to almost about I guess 250 by the time x is equal to 5. Now, an annoying thing again about these graphs is unless I change the scale a bit, it's hard to tell if there's any difference between these guys over here. So let's go ahead and change that scale and change it down to like 0 to just 5 maybe. Now they're both going to run off the scale way before x equals 5, but now you can see a little bit of the difference. Now one thing that's not different is they both have exactly the same value at x equals 0, and that's 2 to the 0 is 1 and 3 to the 0 is 1. That's the common value they have. And now notice the 3 to the x is bigger over here, because 3 like to the 1 is 3, bigger than 2 to the 1 is 2. 3 squared is 9, which is way off here, compared to 2 squared is 4. But they switch roles over here. The 3 to the x is smaller over here, and the 2 to the x is bigger. The way I like to think about it is that there is actually something that's very consistent on both sides. The job of 2 to the x, it has two jobs. For positive x, its job is to get very, very big. For negative x, because that's really a fraction, it's like 1 over 2 to the 4th, its job is to get quite small. It does that job quite well. It gets very small over here, it gets very big over here. 3 to the x, that's this guy, does the job even better. It does both jobs better. It gets big faster and it gets small faster. Because, for example, 1 over 3 squared, that's 3 to the minus 2, that's this point right here, that's going to be 1 over 9. That's smaller. It does a better job of being small than 1/4, which is the corresponding point on 2 to the x. Now, we can try all kinds of other bases, but let's try something else. Let's add one more. Let's do like 1/2 to the x. That's a little bit of a variation on the idea of a different base. We actually use a base that's smaller than 1. Well, what's going to happen here? Let's see if we can guess. If x is like 2 or 3 or 4, you're going to already have a fraction. It's going to be 1 over 2 to the 2, 1 over 2 to the 3, 1 over 2 to the 4. So that's going to be small when x is positive. When x is negative, that negative is going to flip the fraction back and it's going to be big. So it should have the opposite behavior. And indeed, there it is. That's 1/2 to the x. It's exactly the flip of 2 to the x. Now that's interesting. Because we actually had a different way of flipping a function. Let's see if we can add one more. If I have 2 to the x, if that's my function, the way to flip it left and right is just put a minus in front of the x. Let's see what happens when we add that. Nothing happens, because it's actually exactly the same graph as 1/2 to the x. And so that's actually a very important thing about exponential functions, is the way that make them go down is either make the base smaller than 1 or put a minus in front of the x. So there's, in the book, they talk about a lot of transformations you can do with exponential functions, just the usual transformations, but there's some funky things about these guys, like the fact that 2 to the minus x was the same exact thing as 1/2 to the x. That's something that's special, very special to exponential functions. But I don't think I'll go into the details of that right now with this video. Yeah, I think that's a good place to stop this video.